welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, I'm Associate Professor at the Department of Economics of Aligarh Muslim University. Today we will be discussing two concepts. The first one being an impulse response function. This impulse response function, it basically traces the impact of an innovation, or also we called as an impact of a shock on the adjustment part of the variables. We will see this process in detail. Suppose we take this our model in the VAR framework. We take this model in the VAR framework and we can say that yt is equal to lambda 10 plus lambda 11 yt minus 1 plus lambda 12 xt minus 1 plus the error term, the error of y at time t. So the things which we need to see, that the dependent variable is also present as a lagged variable in the independent with the independent variables, and also there is a lagged variable of the xt. So there is no contemporaneous relationship. The explanatory variables are in lag terms. Similarly, our xt, it is a function of yt minus 1 and also a function of lagged values of itself, that is xt minus 1. And these two errors, this is the error for y and the errors for x, we also assume that they are also unrelated with each other. So basically over here there can be two shocks, one on y and the other on x. So when there are two shocks, then there will be four cases. Effect of a shock to y on y, effect of a shock to y on x, then effect of a shock to x on y, and effect of a shock to x on x. So these are the four things we will be seeing in our discussions on impulse response function. So this just for your reference, we have written the VAR model over there. Now suppose it is traditional to say that there is an one standard deviation shock. We do not say one unit shock, but rather we say that there is an one standard deviation shock. So say let there be a one standard deviation shock on y, so that at time t is equal to 1, the error of y is equal to sigma y, that is standard deviation y, and after that the error of y gets a value of 0. So assume that this uyt, that is the error of y, is equal to 0. Then we also assume that y0, that is at the first time period, y0 is equal to x0 is equal to 0. Basically, since we are interested in seeing the how the shocks happen, what is happening after there is a shock, so we can assume that there is no issue. And also the second assumption is, we take that there is, just for the sake of simplicity, we will ignore the intercept terms. So at time t is equal to 1, the impact of a shock of size sigma y on y is y1, that is equal to uy1, this is equal to sigma y, and the effect on x is 0, because the impact on it's on y, so here over here it is 0. Now at time t, at the time period 2, the impact of the shock on y is y2. So this becomes, it was when it was t minus 1, that was a different case. Now here what is happening, t minus 1, so at time period 2 this becomes y1, this becomes x1. That is why we write y2 is equal to lambda 11 y1 plus lambda 12 x1. Now this is equal to lambda 11 sigma y, because this is sigma y, plus lambda 11, this is 0. So what we are left is only this term, that is the impact of the shock on y at time period 2 is equal to lambda 11 sigma y. Similarly, the effect of x, that is on x2, is equal to lambda 11 y1, lambda 11, now this yt minus 1, it becomes, if we reduce 1, so it becomes yt, and so this becomes y1 plus lambda 22 x1. So this we can write as lambda 21 sigma y, and this is 0, because what we have taken over here, the effect on x is equal to 0. So what we are basically seeing over here, that we are assuming that we are starting, that is y0 is equal to x0 is equal to 0. So when t is equal to 1, when t is equal to 1, so this becomes the size, when t is equal to 1, the impact of a shock on size sigma y on y is, y1 is only this much, that is, and in case of x it is 0. When we take time period 2, then what happens, this time period 2, then this becomes lambda 11 y1 and this becomes lambda 12 x1. So these becomes these things. Now again we are seeing the impact is on sigma y, so this we can write as lambda 11 sigma y, and here this is 0, so this becomes 0, the entire thing becomes 0. So this is the first case, and in the second case what happens, this comes over here, lambda 21, it becomes sigma y, and this is again a 0. Now, so we have derived what happens at time 2. At time 2, this is the case, that is y2 is equal to lambda 11 sigma y and x2 is equal to lambda 21 sigma y. Now let us take the case when time is equal to 3. When time is equal to 3, the impact of the shock is equal to, so it will become 1 minus, so it was 3, it will become 3 minus 1, so it becomes 2. So it becomes lambda 11 y2. Same thing over here, t minus 1, that is 3 minus 1, that is equal to 2. So we get x2, lambda 12 x2. Now, y2 we have just now defined as lambda 11 sigma y. So we incorporate this variable over here, we can write it as lambda 11 sigma y. Similarly, we incorporate the value of x2 over here, so it becomes lambda 12 lambda 21 sigma y. Similarly, we repeat the same process for x. So we can write that x3 is equal to lambda 21 y2 plus lambda 22 x2. Now lambda 21 lambda y2, we will write this value. So we can write it as lambda 21 lambda 11 sigma y, and in place of x2 we will write this value. So we can write lambda 22 lambda 21 sigma. Now we will generalize it. We can extend it for period 4, period 5, period 6, but we are just generalizing it. So what we have seen, what was in the first case, in the case of y, it was sigma y, then it became lambda 11 sigma y, then it became lambda 11 sigma y plus lambda 12 lambda 21 sigma y. So these three, what we are doing, we are taking these three and writing in the general form. We are taking sigma y common. So in the first term it was sigma, so we write 1 1. Here it was lambda 1 1, so we get lambda 1 1, and here it was this term, so we are writing it like this. And this can be extended further. So this was the shock to y on y. Now let us see the next case, the shock to y on x. So what was in the first case? It was just a 0. We have seen the derivation before. In the second case it was lambda 2 1 sigma y. In the third case it is this term, lambda 2 1 lambda 1 1 sigma y plus lambda 2 2 lambda 2 1 sigma y. This we write it in the general form as, we just take sigma y common, and here it is 0. This 0 comes over here, this 2 it comes over here, and this term it comes over here. So this is how you write the impulse response function in the general format. Now we have, in our previous case we have discussed the shock to y. Now here we are considering shock to x. So see what happens when there is one standard deviation shock to x at time t is equal to 1. So ux at period 1 is equal to sigma x, and then after that period, after the first period, ux is 0. Now, and say assume uy is equal to 0 for all time t in the first period after the shock. The effect of the shock of the size sigma x on y is y1 is equal to uy, that is equal to 0. And the effect of the shock on x is x1 is equal to ux1 at one time is equal to sigma x. So a one standard deviation shock to x, so that at time t1 is equal to sigma 1 u1x is equal to sigma x, and then after that it becomes 0. So in the first period, the effect of a shock on size sigma x on y is y1 is equal to uy at first time period is equal to 0, and effect of the shock on x is ux, which is equal to sigma x. Now this process, we were repeating the process which we have done earlier in terms of shock to y. So at time is equal to 2, your yt is equal to lambda 1 1 y1 plus lambda 1 2 x1, which is, now this is 0. So this entire terms becomes 0. So you are left with only this term, that is lambda 1 2 sigma x. Similarly, the effect on x is equal to lambda 2 1 y1 plus lambda 2 2 x1. Now again this is equal to 0, so you are left with lambda 2 2 sigma x. So this is at time period 2. So just like we the same case where we have done the repeatedly the substitutions, and we got a general form. So we are not repeating the same process, but if we repeat, we will get the impact of a shock to x on y as sigma x is common, and then you have 0, next term is lambda 1 2, and then it is lambda 1 1 lambda 1 2 plus lambda 1 2 lambda 2 1. Similarly, the impact of a shock to x on x, you take sigma x common, and the remainder of the term is, the first term is 1, then the second term is lambda 2 2, and the third term is lambda 2 1 lambda 1 2 plus lambda 2 2 lambda 2 2. So likewise you can generalize, and you can see the impact of the impact of a shock to the system. So basically this impulse response function shows the magnitude of the impact of the shock along with the rate at which the shock disappears, and at the same time it also considers the interdependence. Now we move on to the next item for discussion, that is the forecast error variance decomposition. Now, this is basically the process of associating the source of the variation in the forecast error. We take our the VAR model, the specification. Now here we assume that there is only one shock that leads to the forecast error. Hence, in the first case, the forecast error variance is 100% due to its own shock. So let us take the first item, yt is equal to lambda 10 plus gamma 11 lambda t minus 1 plus gamma 12. No, this is yt minus 1 plus gamma 12 xt minus 1 plus error of y at time t. Now, the best forecast will be obviously the expected value. So, the forecast for this period is nothing but the expectation of this term. So, the best forecast is the one step ahead forecast. The best one is the expected value. So for the forecast of y at t plus 1, we have taken our initially we were having t, now we are got the value t plus 1. So t plus 1 we can write it as expected value of gamma 11 yt plus gamma 12 xt plus gamma y t plus 1. Now when we take the expectation, this term, because this is an error term, expectation of it is 0, so we are left with only this, that is gamma 11 gamma yt plus gamma 12 xt. Similarly, one step forecast for xt plus 1, this is equal to the expected value of the entire term. Now the term is gamma 21 yt plus gamma 22 xt plus error of x at t plus 1 period. So when we take expectation, this becomes 0. So you are left with gamma 21 yt plus gamma 22 xt. Now again, we need to emphasize that the best one step ahead forecast is what we have seen, and the error is unknown and its conditional expectation is 0. Again, in the first period, all variation in the forecast error for y is due to its own shock. Likewise, 100% of the forecast error for x can be explained by its own shock. Now, the corresponding one step ahead forecast and variance, how do you find the forecast? The yt minus 1 minus expected value of yt plus 1. Not yt, how we can find the forecast? That is equal to yt plus 1 minus the expected value of yt plus 1. The difference between this will be, this is the expected value and the original value. If you see in our previous slide, this is our full term. This one was so what happens? What we are left is when we do yt plus 1 minus expected value of yt plus 1, what is left is only the error uy t plus 1. Similarly, when we do the forecast error for x, that is equal to xt plus 1 minus expected value of xt plus 1, which is equal to the error of x at time period t plus 1. From this you can derive the variance of the forecast error for y is nothing but sigma square y, and variance of the forecast error for x is nothing but sigma square x. So in the first period, all variation in the forecast error for y is due to its own shock. That is, 100% of the forecast error for x can be explained by its own shock. Now, just a brief recap of what we have done. One thing is we have ignored the intercepts. So yt plus 1 can be written as, this is ignored, this is the original equation, this is ignored. So this lambda gamma 1 1 yt minus 1 at t plus 1, this yt minus 1, it becomes yt plus gamma 1 2, this xt minus 1, and when we are taking t plus 1, this will become xt plus error of y at t plus 1. Similarly, for xt plus 1 is equal to gamma 2 1 yt plus gamma 2 2 xt plus error of y at t plus 1. Then we are calculated the forecast error. When we calculate the forecast error, this is my yt plus 1 and the expected value is this much. So this is in the minus sign and this is in the minus sign, this is in the minus sign. This gamma 1 1 yt, gamma 1 1 yt, one is, this is in plus and this is minus, so it cancelled. Gamma 1 2 xt minus sign, gamma 1 2 xt plus sign, this also cancelled, so you are left with error of y at t plus 1. Same thing for forecast error of x. We have xt plus 1 minus expected value of xt plus 1. So xt plus 1 is this term, that is gamma 2 1 yt plus gamma 2 2 xt plus error of x at t plus 1, and expected value of x t plus 1 is equal to gamma 2 1 yt plus gamma 2 2 xt. Now what happens? Again, this is in minus, this is in minus, so this term and this term cancels out, and gamma 2 2 and gamma 2 2 here also cancels out. So I am left with error of u x, error of x t plus 1. So this is error of x t plus 1. So the corresponding one step variance from this, you can find it as sigma square y and sigma square x. Now, so we have the function of yt, we have the function of xt, we have seen just before. Then we derived this xt plus 1 and we derived this yt plus 1 and xt plus 1. Now we take 2 steps forward. So when you are taking 2 steps forward, this becomes xt plus 2, and herein it was t and we add one more. Herein it was t, we add one more, or from here we add 2 more and we get t plus 1. Similarly, error of y t at t plus 2. Similarly, for xt plus 2, we get this function. So this was yt and then we increased to yt plus 1. This was xt, we increased to xt plus 1. And then we have the error of x at time period t plus 2. So we are just showing that this is yt and xt, this is yt plus 1 and xt plus 1, this is yt plus 2 and xt plus 2. Now, we will go for 2 steps ahead for y. Now here we have just ignoring the intercept term for simplicity. Now the forecast of yt plus 2 is, we have seen, we'll take for forecast, we take the expectations. So we have just now derived this yt plus 2, we simply write it here. Expected value of gamma 1 1 yt plus 1 plus gamma 1 2 yt xt plus 1 plus error of yt at t plus 2. Now gamma yt plus 1 has been earlier defined over here. We substitute these values. So upon substituting, what we can write, gamma 1 1, and in place of yt plus 1 we write gamma 1 1 yt plus gamma 1 2 xt plus error of y at t plus 1. Similarly, the next term is gamma 1 2 xt plus 1. Xt plus 1 we have over here. This term we are incorporating over here. So we have gamma 1 2 multiplied by gamma 2 1 yt plus gamma 2 2 xt plus error of x at t plus 1 plus our original error term, that is error of y at t plus 2. What we do, we can then just open the bracket and remove the expectations. We take the expectations, so we are left with this term vanishes, this term vanishes, this term vanishes. When we take expectation, all the error terms, they become 0. So what we are left with, gamma 1 1 multiplied by gamma 1 1 yt plus gamma 1 2 xt plus gamma 1 2 multiplied by gamma 2 1 yt plus gamma 2 2 xt. Now, similarly, we will derive the two step ahead for x also. So, x forecast t plus 2 is equal to the expectation of, now xt plus 2 we have over here. This is nothing but our xt plus 2. So what we write, we incorporate in place of yt plus 1, we incorporate the term. In place of xt plus 1, we incorporate this term. And then we have this our error term, it coming over here. Here this gamma 21 is coming over here, gamma 22 is coming over here. After this, we simply take the expectation. The moment we take the expectation, we are basically repeating the same process which we have done for y, forecast of y at t plus 2. This becomes 0, this becomes 0, this becomes 0. All the error terms become 0. So we are left with gamma 21 multiplied by gamma 11 yt plus gamma 12 xt plus gamma 22 multiplied by gamma 21 yt plus gamma 22 xt. Now we have done the forecast. Now we will see two step ahead forecast error and variance. Forecast error is nothing but yt plus 2, forecast error for 2 period, minus the expected value of yt plus 2. All these things we have just now derived in our previous slide. So we are just in place of yt plus 2, we write the term from here to here. That is gamma 11 square yt plus gamma 11 yt xt plus gamma 11 error of y t plus 2 gamma 21 gamma 2 gamma 12 gamma 21 yt plus gamma 12 gamma 22 xt plus gamma 12 error of error of x at t plus 2 and error of y at t plus 2 minus, this is the expectation value, minus then we have it in bracket gamma square 11 yt plus gamma 11 gamma 12 xt plus gamma 12 gamma 21 yt plus gamma 12 gamma 22 xt. This is in minus, this is in minus, this is in minus, this is in minus. So this and this term is cancelling out. Again, this is also in minus, this term and this term is cancelling out. This 1 2 and 2 1 yt, this and this term is cancelling out. Here gamma 1 2 gamma xt, this and gamma 1 2 gamma xt is cancelling out. So we are left only with the error terms. This is the one error term, this is the another error term, and this is the third error term. We are left with these three error terms. So this comes over here, this comes over here, and this comes over here. So the forecast error is equal to gamma 11 error of y at t plus 2, gamma 12 error of x at t plus 1, then gamma gamma, and then the third term is error of y at t plus 2. There is a small mistake, please correct it. This will be this will be 2, not 1 over here. This and this term are the same, so there is a typo error over here, so it will be 2. Now from this error we can find the variance, square it. So what we get, the variance, gamma 11 square sigma square y gamma 12 square sigma square x plus sigma square y. We will repeat the same process, and we will get the forecast error. We'll get this is we get it by xt plus 2 minus expected value of xt plus 2. This is equal to gamma 21 error of y t plus 1 plus gamma 22 error of x t plus 1 plus error of x at t plus 2. Now we can, from this forecast error, we derive the variance. Variance is equal to gamma 21 square sigma square y gamma 22 square sigma square x plus gamma x square. So Once we have derived this, we can say that the total variance of the forecast process and variance of the forecast for y is equal to gamma 11 square gamma square y plus gamma 12 square gamma square x plus gamma square y. Now we can decompose this. Now see, we decompose it due to shock to y, that is own shock. We are seeing the shock of y on y. So this we can write it as this term gamma 11 square sigma square and this plus sigma square y divided by this entire term. So this is the shock. This is when we have decomposed the error due to the shock on y. This is gamma 11 square sigma square y plus sigma square y divided by this entire thing, that is gamma 11 square sigma square y plus gamma 12 square sigma square x plus sigma square y. The same thing can be repeated. Then when we are seeing the decomposed error due to the shock to x only, that is the shock of other. Earlier it was shock of y on y, the same variable, own shock. Now we are saying shock of x. So this thing we can write it as, now this is the middle term, this you can write as a ratio. What is due to the shock to x, we can write it as gamma 12 square sigma square y divided by this whole term, that is equal to gamma 11 square sigma square y plus gamma 12 square sigma x square plus sigma y square. So similarly, what we can do, we can this two-step forecast variance of x due to its own shock. We are not going for again the derivation, we have already seen. So we will repeat the same process. So here we get gamma 22 square gamma sigma square sigma x square plus sigma x square divided by gamma 21 square sigma square y plus gamma 22 square sigma x square plus sigma x square. And the forecast error of x explained by other shock is gamma 21 square sigma square y divided by gamma 21 square sigma square y plus gamma 22 square sigma x square plus sigma x square. So basically, this variance decomposition analysis gives information about the source of volatility. It shows that the variance of forecast error increases as we increase the forecast horizon. There is only one shock that leads to this forecast error. Hence, the forecast error variance is 100% due to its own shock. Now, this exercise in the first case, then it changes. This exercise of attributing the source of the variation in the forecast error is called as variance decomposition. So we can quickly say in the first step, we can say that in the first step the variance was sigma square y and sigma square x. And when we go to the two-step variance, it is gamma 11 square sigma y square plus gamma 12 square sigma x square plus sigma y square, and variance of the variance of forecast error at two step is equal to gamma 21 square sigma y square plus gamma 22 square sigma x square plus sigma x square. So in the first period, the variation in the forecast error for y is due to its own shock. So 100% of the forecast error for x can be explained by its own shock in the first step variance. But when we go to the next step, it changes. And similarly, when we go to the third step and the fourth step, it will keep on changing. So this is what we refer to variance decomposition. So we have discussed these two cases of impulse response function and variance decomposition. Hope this lecture was clear to you. Thank you.